In this lesson, we'll talk about double angle, half angle, and power-reducing identities. So, more identities. Let's recall the double angle identity for cosine. Cosine 2 theta is the square of cosine minus square of sine. And we also mentioned that this identity can be presented in three different forms. Cosine of 2 theta is equal this much, or it could be equal 2 cosine square minus 1, or 1 minus 2 sine square. I actually already showed these two identities in the last lecture, so this time it's a good practice for you to do this exercise by yourself. To prove this identity, it's enough to replace sine square by 1 minus cosine square, so we'll have cos 2 theta equals cos square theta minus, and instead of sine square, we can write 1 minus cosine square from Pythagorean identity. Then we have cos square, and 2 minuses makes it plus another cos square, so we really have 2 cos square theta minus 1. So this identity is proven. Similarly, to prove this version, it's enough to change cosine square in the original version into 1 minus sine square. So let's try it again. Cosine 2 theta is 1 minus sine square theta. That's instead of cosine square. And then minus another sine square theta. So altogether it's 1 minus 2 sines square theta. So yes, this also works. Again, the most commonly used identity for cosine double angle is cosine square minus sine square, but occasionally it's a good idea to know that we can express this in terms of just cosine or just sine. So 3 formulas. And here we have a list of double angle identities. So as we remember, sine double angle is 2 sine cosine. Cosine double angle, we just talked about this here. And tangent double angle is 2 tangent over 1 minus tangent square. That was proven in the last lecture. Now from this double angle identity for cosine, we can actually derive identities for sine square or cosine square. So those will be called power-reducing identities. For example, if I solve this equation for sine square, so imagine bringing the term negative 2 sine square to the left and cosine double angle to the right, and finally divide by 2, that will produce this first identity. It's a power reducing because we change sine square into a single function without any squares. That will be quite useful in second calculus course when you will be asked to calculate integrals of, for example, sine square. So integrals of square of a function won't be easy to do, but if you bring it into a single function, it will be doable. From the same row, if we solve this equation in green for cosine square, then we obtain the second identity. Cosine square is 1 plus cosine double angle over 2. So that will be the green one. And to come up with the power-reducing identity for tangent, it's just enough to divide sine square over cosine square. So if we divide these expressions, then the 2 will cancel and you will end up with 1 minus cosine double angle over 1 plus cosine double angle. So that's tangent. And the next bunch of identities, I will leave it up to you to check. It's enough to replace theta by theta half in power-reducing identities and then take square root on both sides to obtain identities for half angle. So sine of half angle is, since we're taking square root, then we have to use plus or minus sign. The decision as to which sign to take should be done by just looking at the angle pi half, in which quadrant this angle happened to be. So We know that sine is positive in the first two quadrants, so if theta half is from 0 to 180, then we use positive, otherwise we use negative. Similarly, we develop formula for cosine half angle, again using power reducing identities and taking square root on both sides. And finally, tangent of theta half. Well, tangent of theta half is basically the same as sine of theta half over cosine of theta half. So as you see, the two will be reduced and we'll end up with root of 1 minus cosine over 1 plus cosine up to the sine. Again, you determine the sine by looking at which quadrant we have our theta half. Since this formula is kind of big, sometimes it's more convenient to use these two results. So tangent of half angle could be expressed as sine over 1 plus cosine or 1 minus cosine over sine. And we are going to show that these expressions are equivalent. So in this exercise, we are asked to show that these two expressions are exactly the same. Well, let's consider square root of 1 minus cos theta over 1 plus cos theta. If I wish to get rid of the root and change this expression to that form, it's a good idea to have a perfect square of something. So, if we multiply the top and the bottom by a conjugate of a numerator, 1 plus cosine theta, and the bottom the same, then we end up with root of 1 minus cos square theta, and in the bottom 1 plus cosine theta bracket square. Since in the numerator we really have root of 1 minus cosine square is sine square, and the denominator, the root cancels the square and we really have 1 plus cosine theta. Since 1 plus cosine theta is always bigger equals 0, then we don't have to worry about using the plus minus sign here. And then root of sine square theta is the same as absolute value of sine theta over 1 plus cosine theta. So as you see, we end up with the same expression as we wanted, except for this absolute value. Well, let's analyze sine. The left-hand side is positive for theta half being in the first quadrant. But if theta half is in first quadrant, then theta by itself is actually in the first two quadrants. But that means that our sine theta is also positive. So this expression sine theta over 1 plus cosine theta agree as a matter of sign with the left hand side. It's for plus. Now what's happened with minus? Well, this expression is negative if theta half is in the second quadrant, but then theta by itself is in the third or fourth quadrant. That means it will also become negative. So we don't really have to use this absolute value because the sine of theta matches those two signs for the expression of tangent theta half. That means for this expression. Okay, therefore we can use this plus or minus all the way along, and then we don't have to use the absolute value. So this identity really holds. Now to prove the second identity, we can basically perform nearly the same calculation. So for now, forget about plus minus. You can justify this at the end that the sign will agree for both expressions, but just generally the whole expression, if we multiply the top and the bottom by a conjugate of the denominator, 1 minus cosine theta in the bottom and in the top, then we end up with the formula. This will be 1 minus cosine bracket square and take square root, so it's just 1 minus cosine. So that's exactly what we wished for. and in the bottom it will be square root of 1 minus cosine square, which is the same as sine square. So yes, we end up with 1 minus cosine theta over formally absolute value of sine theta. But then if we apply plus or minus on this side, this absolute value doesn't have to be written. And again, you can check on this on your own. So that's the same as 1 minus cosine theta over sine theta. To analyze the sign, similarly as in the previous case, first notice that 1 minus cosine will always be bigger equal 0. It's never negative. Therefore, the sign of this expression really depends on sine theta. So the argument about agreement with sign, plus here and plus there, minus here and minus there, is exactly the same as in the previous case. In the next exercise, we are asked to rewrite this expression in terms of a single trig function. So the pattern that I observe here is a difference of squares, square of cosine and square of sine, of the same angle, which really tells me that I can fold it back to the double angle formula. This is the same as cosine of double of this angle. So cosine of 2 times 5 theta, which is the same as just cosine 10 theta. So that was actually easy if you recognize the formula. And let's see what do we have in this example. Knowing that cosine of certain angle alpha is given 5, 6, and alpha is in the 4th quadrant, so alpha is in the 4th quadrant, find the exact value of sine double angle, cosine double angle, and so on. So sine double angle, let's rewrite this to a single angle function. That would be 2 sine alpha cosine alpha. Fantastic. So we know cosine alpha, this can be replaced at once, but we need to find out what sine alpha is. Well, let's draw the modeling triangle as usual, right angle triangle here. And if this is angle alpha and cosine alpha is 5 over 6, then this side must be 5 and that's 6. So the third side can be found from Pythagorean equation. This will be square root of 6 squared, which is 36, minus 5 squared, which is 25. So it's really square root of 11. Okay, therefore we can figure out what sine of this angle is a root 11 over 6. And since alpha is in the 4th quadrant, sine will be negative. So we end up with 2 times negative root 11 over 6 times cosine alpha, which is 5, 6. So altogether, if we reduce this 2 with one of the 6's, we end up with negative 5 root 11 over 18. That's the final exact answer. Okay, let's do the same for cosine double angle. Cosine double angle is the same as cosine square alpha minus sine square alpha. And since we already know the values for both sine and cosine from step A, cosine because it's given in a problem, 5, 6 square, and sine is negative root 11 over 6. And that's squared as well. So we end up with 25/36 minus 11 over 36. Altogether, 25 minus 11 is 14/36, and we are able to reduce this by 2, so it will end up with 7/18. Final answer. Okay, how do we calculate tangent double angle? Well, we can follow the formula for tangent double angle, but we can also use the previous values because we know that tangent is the same as sine double angle over cosine double angle, and both of these values we already have. So let's make use of it. Sine is negative 5 root 11 over 18. and then divide, meaning multiply by reciprocal of cosine, which is 18/7. That's nice. We can reduce the 18 and we end up with negative 5√11/7. Final answer. Okay, now to calculate sine of half angle, let's recall the formula for half angle, which is here. So sine of alpha half is plus or minus. How can we make this decision? Well, if alpha is in the fourth quadrant, then alpha half will be somewhere in the second quadrant, because half of 360, the top number will be 180 and the bottom number will be 135. So it is in the second quadrant. Alpha half is in the second quadrant. Okay, sine in the second quadrant is positive, so we use the positive part of this formula. Square root of 1 minus cosine alpha, not alpha half anymore, but alpha. So let's record this, cosine alpha over 2. And we know what cosine alpha is because that was given in a problem. So it's 1 minus 5/6 over 2. So the rest is just to simplify this expression. That will be 6/6 minus 5/6, so it's 1/6. And then divide by 2 means multiply by 1/2. And then square root. So that's the same as square root of 1 is 1, square root of 12 is 2√3 when we simplify the bottom. And now, since we don't like irrationality, we multiply top and the bottom by √3, ending up with √3 over 2 times 3 is 6. Final answer. Well, let's calculate cosine of half angle. Again, I will encourage you to stop the video and try on your own. At least some of those exercises, try on your own. If you have any problem or if you want to check the answer, then watch the video. Cosine alpha half. Well, if alpha half is in the second quadrant, cosine is negative. So we need to use the negative portion of this formula. Negative root of 1 plus cosine alpha over 2 equals. So negative root of 1 plus cosine alpha is 5/6 over 2. And simplify as before. So we have 6/6 plus 5/6 is 11/6. And then instead of dividing by 2, multiply by 1/2. And that gives us negative root 11 over root 12, which again is 2√3. Multiply the top and the bottom by √3 to get rid of irrationality, and we end up with negative root 33 over 6. Final answer. Finally, tangent of half angle. Well, that's the same as sine over cosine of half angle. Therefore, we can just use the values that we already have for sine and cosine of half angle. So sine is √3 over 6. Divide means multiply by reciprocal, so it will be negative 6 over √33. We can reduce the 6's, so we have negative √3 over 33, and we can reduce again the 3 with 33, leaving with 11 in the bottom. So we end up with negative 1 over √11. And if we get rid of irrationality, multiplying by √11 here and there, we end up with negative √11 over 11 as a final answer. In this exercise, we are asked to rewrite the fourth power of cosine in terms of first power of cosine function using appropriate power reducing identity. Just for our recollection, this is the identity that will be helpful. Well, we don't have cosine square, we have cosine to the 4. However, this could be written as cosine square x and then square it again. Since cosine square x, according to this formula, is equal 1 plus cosine double angle, so 2x over 2, Then, after squaring, we perform perfect square in the numerator, so we get 1 plus double the product 2 cosine 2x and plus cosine square 2x. Everything over 4. Okay, so we decreased the exponent 4 to a first power and also the second power. Now we still need to take care of this part because the question calls for first power of cosine function. So we need to apply this identity again. We may want to write the 1/4 in front of everything because that seems to be easier. And then we have 1 plus 2 cosine 2x, and from the identity 1 plus cosine double this angle 2x, which is actually 4x, over 2. Now if we pull the 1/2 out of the bracket, we'll end up with 1/8, but then these two terms will have to be multiplied by 2. So we have 2 plus 4 cosine 2x, and then plus 1 and plus cosine 4x. Oh, this expression involves only cosines and in the first power. So yes, we've done the job. The only thing that we can still do is to collect the 1 with 2. So the final answer will be 1/8, and then it's 3 plus 4 cosine double angle plus cosine 4 times the angle. In the next exercise, we are going to use half-angle identities in order to find exact values of the following trig functions. So the first one is cosine 105. Well, if we use the half-angle identity that is here, cosine of half-angle, so treat 105 as half-angle of theta, and taking in consideration that this half angle 105 degrees is in second quadrant, we'll use the negative root. So this will be negative root of 1 plus cosine of the full angle, which is double this angle, 210. Everything over 2. Now, to figure out the exact value of 210, we need to recall the reference angle. So the reference angle for 210, which is somewhere here, is 210 minus 80, which is 30 degrees. Therefore, this expression is negative root 1 plus cosine of the angle in the third quadrant is negative. So instead of cosine 210, we'll write negative cosine of the reference angle, which is 30. Everything over 2. Okay, the exact value of cosine 30 we'll take from special triangle, half of equilateral triangle. This is 1, 2, root 3, and 30 degrees is this angle, so cosine 30 is root 3 over 2. Therefore, we have negative 1 minus root 3 over 2, and everything over 2 again. So let's see 1 as 2 halves. So under common denominator we'll have 2 minus root 3, and then divided by this 2, and then divide by another 2, so it's divided by 4. And we have square root with minus here. Therefore, we can split the root over numerator and denominator. We'll end up with negative root of 2 minus root 3, everything over 2. Exact answer. Okay, let's see the second case. We need to calculate tangent of 67.5. Since this angle is in the first quadrant, tangent is positive, so we use one of the formulas that refer to tangent of half angle. I would suggest to use the last one because it seems to be the simplest. Therefore, we have 1 minus cosine of double of this angle, which is 135, over sine of 135. Now, since 135 is in the second quadrant, therefore we can rewrite this as 1 plus, because cosine in second quadrant will be negative, and this negative altogether plus cosine of the reference angle. And the reference angle is 180 minus 135, which is 45. Everything over. Sine in second quadrant is positive, so we can just replace it by sine 45. And now we remember what's the value of cosine or sine 45. It is root 2 over 2 and over root 2 over 2. What's left to do is to simplify this complex fraction. We could multiply the top and the bottom by 2. That gives us 2 plus root 2 over root 2. And finally, to get rid of irrationality, multiply the top and the bottom by root 2. That becomes 2 root 2 plus 2 over 2. Well, we can do one more step. We could reduce the 2's by factoring it out with the 2 in the bottom, so that makes it 1. So the final answer is just root 2 plus 1. Now let's try sine of 9 pi eighths. Well, since 9 pi eighths has a reference angle pi eighths, and 9 pi eighths is actually in the third quadrant, that makes sine negative. So all this stuff can be written as negative sine of pi eighths. And now we can use half angle identity. This time the angle is in the first quadrant. We don't have to worry about sine, it's positive. So we simply write this is negative square root of 1 minus cosine pi quarter, because we take double this angle, everything over 2. Okay, and now we can easily replace the pi quarter. We know the value. As before, this is minus root 2 over 2 and over 2 again. So we have negative root, and then we have 2 minus root 2 over, and there's over this 2 and another 2, so it's really 4, equals negative root 2 minus root 2, everything over 2. And that's the final exact answer. The last example, cosine 5 pi twelfths. Well, that's before. Let's follow the cosine of half angle. But this angle, as you can see, it's less than pi half. Therefore, this is in first quadrant. So we use the positive branch of this identity. Okay, so it's positive root of 1 plus cosine of double this angle. Double 5 pi 12 is 5 pi 6. Everything over 2. Now, since 5 pi 6 is actually in the second quadrant, we need to rewrite this as negative cosine of the reference angle, and the reference angle is pi 6 over 2. Okay, let's recall the special triangle, 1, 2, root 3. Pi 6 is the small angle, so cosine of it is root 3 over 2. So we have root 1 minus root 3 over 2, everything over 2. So similarly as before, when we calculate this, we end up with 2 minus root 3 over 4, and finally just root 2 minus root 3 over 2. Okay, here's the final answer. As you see, this answer is nearly the same as that one, except that the sign is opposite. And it's not much of a surprise, because this angle has a reference angle of 30, and here we also had a reference angle of 30, just different quadrants. The last exercise is to verify identities, and here we have couple identities that involve double angle or half angle formulas. Let's look at the first one. If I start with the left side, I have 1 over 1 minus cosine double angle. I don't want this double angle here because the right hand side doesn't have any double angles. So let's use one of those formulas for cosine of double angle. I'm going to use 1 minus 2 sine square of single angle. Why? Because I predict that on the right-hand side, cosecant has denominator sine. Cosecant is 1 over sine. So it's a good idea to have sine in this formula. And as you see, when we reduce the ones, we really have 1 over 2 sine square x, which is exactly the same as the right-hand side, cosecant square x, right side. So it's proven. The second example, let's rewrite the left side according to one of those formulas. And since cosecant and cotangent has denominator sine, then maybe the last formula would be the best. Let's see. So we can rewrite this as 1 minus cosine x over sine x. And then if we split this into two fractions, we have directly the right-hand side. So it's not too difficult. So we end up with cosecant x minus cotangent x, which is our right side. Yes, it's proven. And finally, the left side of this identity is cosine square of something minus sine square of something. That's a typical formula for cosine double angle. So this is the same as cosine double the x half, which is just x. Okay, so we know that the left-hand side is just cosine x. Let's figure out what the right-hand side is. So let's try to maybe analyze both sides simultaneously. So the right-hand side looks like it's 1/2. Cosecant is 1 over sine x. And sine double angle is 2 sine cosine. Oh, well, that's great, because sine cancels and 2 cancels, and yes, this is the same cosine. So the left side equals right side. Again, the identity is proven. So as you see, some questions involve a lot of calculations, like the previous slide was pretty heavy. On the other hand, some other questions, like these ones, they look complicated, but they are pretty simple overall.